Hi, my name is Alark Saxena, and I'm the Program Director for Yale Himalaya Initiative. I'm also a faculty here at the School of Forestry and Environmental Studies. Today we have Professor Ed Cook from Columbia University. Welcome.
Thank you, Alark. I'm very happy to be here.
Wonderful. Please tell us a little bit about yourself.
Well, I've been working for Columbia University and actually Lamont Doherty Earth Observatory, an earth sciences research facility, part of Columbia, for 41 years. In 1975, I helped establish a tree ring research laboratory there at Lamont to study primarily climate change, global warming, as it were, or anything else that might allow us to use tree rings to tell us about climate as it's happening now and has happened in the past. And that work's been going on, as I say, for 41 years now, and we're one of the certainly one of the top tree ring research laboratories in the country, if not the world.
Wonderful. That's fascinating. In the 70s, very few people were even thinking probably about climate change. How did it start?
Well, there was a realization even back in the 1970s that the world was getting warmer. A very famous geochemist, Wally Broker, at Lamont Doherty, who's a world's expert in carbon cycle modeling and that sort of thing, realized that yes, the world's getting warmer, and it's probably being driven by elevated carbon dioxide concentration in the atmosphere. But there was still a lot of uncertainties about it. And he was interested in trying to get a much better understanding of the large-scale pattern of variability of climate change and temperature warming, both now and in the past. The instrumental climate records are typically, we'll say for argument's sake, 100 years long, globally at best. And if you're looking for trends in climate, 100 years isn't enough to really define the longer term properties of climate variability and temperature warming. So we know that trees in certain growth environments can provide information about temperature. Trees growing in high elevations, in the Himalayas for that matter. Trees growing at northern tree lines, the boreal forest tree lines of, say, the northern hemisphere. And these trees can live for hundreds of years in some cases, in rare cases, even over 1,000 years. And so they provide us with, by looking at the ring with variations in these old trees growing in these temperature-limited environments, we're able to extract information about how temperatures have changed back 1,000 years or more even, and that provides us with a context to compare against what's happening today with respect to climate warming.
That's incredible, and especially with such kind of information at the ground level, that could be very, very interesting. I'm obviously very curious about your Himalaya work, but I want to just generally think of could you tell us a little bit more about the landscapes that you have worked collecting information, especially on tree rings?
Well, I've spent quite a bit of time developing tree ring networks. In other words, tree ring chronologies from a variety of locations in eastern North America. And I've worked with colleagues at the University of Arizona, University of Arkansas, to piece together a large network of tree ring chronologies across most of North America. We can use those tree ring chronologies not to reconstruct temperature per se, but look at drought, long-term drought variability in the past. And I've spent a good part of my career developing what I call drought atlases, which provide us with both a spatial and temporal history of drought variability extending back 1,000 years or more. North America, in what I call the monsoon Asia part of Asia, China, India, Southeast Asia, and then quite recently Europe, North Africa, and the Middle East. And so we can use that information to understand what we call hydroclimatic variability and how it's changing today versus how it has behaved in the past. And this again provides us with a long-term context with respect to better understanding, are we going into an unprecedented period of climate variability and change now compared to the past?
That's very interesting. Just from my sake and for viewers' sake, could you talk a little bit about how does the weather affect the tree's growth and its hence the rings?
Well, we're talking about trees that put on distinct annual rings, a distinct annual ring per year. Okay. Typically, when you look at the patterns of ring width in a tree that's lived for hundreds of years, they vary in width from year to year. Some of that variation has to do just with biological processes. The tree getting older, for example, will tend to produce a long-term trend in growth that's really not due to climate. But there is higher frequency variability in ring width that is driven, in part anyway, by changes in the growth environment of the tree related to climate. Is it warm? Is it cold? Is it dry? Is it wet?
Right.
That information is what we utilize primarily. There are other sources of information one can derive from tree rings, from wood properties of trees, but the main thing we work with is the variations in ring width.
That's great. Could you talk to us a little bit more about your drought atlas that you've worked on?
Yeah, sure. Yeah. I first developed a drought atlas for North America back in 2004, and it goes back on the order of 1,000 years or more in many places of the country. It's a gridded drought atlas, so literally you can produce maps every year. You can produce a map of patterns of wetness and dryness across North America.
Wow.
And when you do that, and you start looking back further in time to medieval times, for example, 1,000 years in the past, what you find is kind of scary. You find evidence for what we call mega droughts. These are droughts that last for decades or even centuries, they're droughts that have never been seen in the instrumental climate records we have today. They go back about 100 years.
Wow.
But they're present in the tree ring reconstructions of drought and wetness back, into medieval times. It's kind of scary because there's no unusual radiative forcing due to CO2 going on back in medieval times. That's back in a period that's so-called, the background CO2 level of maybe 270 parts per million. Now we're up around 400 parts per million.
Right.
Okay. Now, the argument now is that, of course, the elevated CO2 is producing climate variability that could induce a more droughty future for us, be hotter and drier in some areas. But back then, in medieval times, there was no need for any kind of sort of radiative force from elevated CO2. There was just natural variability that could, in fact, sometimes manifest itself in terms of drought and mega droughts. We don't understand how that happens, but it's a very worrying thing because it says even under natural climate variability conditions without elevated CO2, the climate system has an inherent capability of getting into a mega drought mode of variability. And that's kind of scary because if we got into that mode of variability in the future, the impacts on humanity would be massive.
Massive. And if the current climate change impact further exacerbates that could even...
That's right. That's exactly right. Yes. Yeah. There's no question about that.
Right.
So, and these drought atlases, I've produced now 4 drought atlases. One for, again, North America, the monsoon Asia region, Europe, North Africa, Middle East, and Eastern Australia and New Zealand. And we're now working on a new drought atlas for South America. So we're beginning to piece together almost a global picture of hotter climatic variability that will enable us to compare regions and look for similarities and differences in the timing of droughts and wetness, and that might tell us more about the underlying climate dynamics that are responsible for these patterns of variability.
It's fascinating. I'm really curious to look at some of these atlases. Just as a quick point of clarification, so when we estimate the weather conditions and patterns through the tree rings, how do you let's say call ground truth it, or how do you establish that it's correct or not? What?
Yeah, it's a statistical modeling game that we go through, in which we use basically regression analysis methods to estimate climate from tree rings. Now, in any kind of statistical modeling game like that, there's always a chance that the model will produce inaccurate results. So what we typically do is develop our model over only a portion of the instrumental period that we're using for calibration, as we call it, and then we withhold a portion of the instrumental data from the modeling calibration exercise, and then compare the tree ring estimates of the climate variable in question against the withheld data, and say, do we have accurate results or not? If we don't have accurate results, then we say, okay, well, something is wrong. We don't have a good reconstruction. But if we have, if the tree ring estimates match to a reasonably decent degree the properties of the actual climate data withheld from the calibration period, then we can say that we've produced a verifiable reconstruction that we can then use for other studies.
Yeah, that's great.
Yeah.
And does your data get compared or evaluated to the ice core data, or is there a comparison in that, or it's a little two different different scales?
Yeah, they're pretty different in general. No, I mean, there's been a couple examples I could come up with, but no, that generally not, because the ice core data, represents a little different story than the tree rings. And the ice core data are from very geographically restricted locations, at least in the northern hemisphere. You know, Greenland, basically. Southern hemisphere, mostly Antarctica.
Right.
And whereas the tree ring-based drought atlases, for example, are from temperate to boreal latitude continental land areas.
Right.
That really quite large in scale. So they're really quite different. However, there is temperature information in ice cores. In the stable isotope ratios, for example, of the ice, and that can be compared to temperature estimates from tree rings.
Right.
So in that sense, there can be a useful comparison made, without question.
Right.
Yeah.
And what about the lake sediments that have also been studied? And I'm it's exciting to see that, because there are these different sets of data that are coming in. I'm wondering if there's a way for calibrating or even understanding how close they are.
Yeah, no, there's been some success in comparing lake sediment records. There might be pollen. It could be charcoal in the lakes indicating dry periods and fires. It could be testate amoebas. There are different things that record different chemical properties, or like salinity levels of the water, that represent a period of wetness and dryness, and they can be compared to tree ring series that are also providing some estimate of wetness and dryness in the ringlets.
Right.
So that's in North America. That's been done actually fairly often.
Okay.
The big advantage with the tree ring drought atlas is that the tree rings are exactly dated. The exact counter year formation is assigned to each annual ring.
Right.
And that provides us with an unprecedented or unparalleled precision with respect to the timing of droughts and wet periods, things like that. You get into lakes, for example. Well, the dating is not quite so good.
Right.
I mean, it could be, plus or minus 10 years, plus or minus 20 years, but it's still not going to be exact.
As close as tree ring data.
Yeah, right. So that means that comparisons can be a little bit fuzzy sometimes. The trees are saying something happened in the 1800s, 1850, we'll say, and the sediment core from a lake says, well, it's somewhere between 1830 and 1870.
Right, right.
Yeah.
So the precision increases very, very dramatically if you're using tree ring specifically.
Oh yeah,
right?
No, without question. Yeah.
Right.
Yeah.
So thank you for giving this kind of broad overview of the work that you're doing. And I'm really curious about now the work, especially with your drought atlas that you developed for monsoon. Um, maybe love to hear what were some interesting findings if you from the atlas.
Well, in 2005, our lab at Lamont received funding from the National Science Foundation to develop basically a drought atlas for the monsoon Asia area of the world, and this primarily means India, Pakistan, China, Southeast Asian countries, that sort of thing. And it's a complicated area because there isn't just a single monsoon. You hear all about the Indian monsoon, the Southwest monsoon, but there's an East Asian monsoon, there's a Northwest monsoon, there's a variety of kind of monsoon patterns of variability.
Right.
So what it means is that you can't just develop a tree ring series, say from central India, and say, oh, here's the story about the monsoon.
Right.
Going back, and that might apply to China. Well, that doesn't work that way. So you have to develop, again, this kind of spatial pattern of drought and wetness from the tree rings that can tell you about the what I call the Asian monsoon complex. The different sources of monsoon variability, different kinds of monsoons that happen. And so we worked on that really hard. It's not an easy place to work in, I should say. There's not a lot of old forest in many parts of Southeast Asia. Sometimes you're lucky to get 300 years of record from trees that are still on the landscape. But in 2010, we did have a sufficient network of tree ring chronology developed there where we could actually develop a drought atlas based on what's called the Palmer Drought Severity Index, which is a measure. It's a drought index that takes into account both. It's a soil moisture balance model that takes into account both wet and dry, components of the hydrologic system, and incorporates evapotranspiration demand and things like that in the estimates, besides just how much it rains. But the point is that 2010 we published the Monsoon Asia Drought Atlas in the Journal of Science, and I certainly encourage you to look at the paper because it shows some of the efforts we made to try to validate the estimates back in time. The climate data in the South in India has wonderful climate data, some of the best in the world. The British, God bless them, when they were in the colonial power there in India, set up meteorological stations, recording temperature and precipitation. Going back into the 1800s, back in the 1870s and like that, the All India Monsoon Index, for example. But there's nowhere else in Asia that's like that. And like all of China, for example, most of China has no local meteorological data before 1950. It's only after Mao Zedong took over China that he decreed that a whole network of weather stations shall be established in China. So it's a difficult area to work in from the point of view of calibration. Calibrating the tree rings in terms of the Palmer Drought Severity Index, for example. And so we wanted, and it was hard to validate the estimates, but there's a lot of historical data in Asia too, historical data that refers to climate events.
Right.
There's the Great Victorian Holocaust drought in India, for example, that from 1876, 77, 78 led to massive deaths.
Yeah.
Then there's the 1790s drought in India, that is recorded. The Ming Dynasty drought in China. It was a relatively short-term drought in China, but it led to a destabilization and collapse of the Ming Dynasty because it was a severe drought where the people were living up near the Beijing area, and the emperor was considered to be divine at a certain level, and yet he allowed this to happen to the people, and it led to the collapse of the dynasty. And we were able to show that the Monsoon Asia Drought Atlas actually preserved that information in its estimates.
Wow.
About the timing of the drought that led to the collapse of the Ming Dynasty.
Wow.
So we found evidence for Well, you've heard probably of Angkor Wat
Yeah.
in Cambodia, the Khmer civilization in what's now Cambodia, flourished in the the 1100s, 1200s, 1300s, and then went into a very steep decline and a depopulation of Angkor. And there's always been a lot of speculation about what happened there, whether or not it was an invasion, for example, of other peoples. Brendan Buckley at our lab has published on this, and the monsoon Asia drought out this showed that there was a couple of extremely serious droughts that in the 1300s and 1400s, that the timing was almost perfect for what is known about the timing of the abandonment of Angkor, by the Khmer people there. So there was really good evidence now that mega droughts in the period right around the time of the decline and demise of the Angkor civilization, Khmer civilization in Angkor, happened.
Right.
And so Brendan argued, I think, and it's been pretty well accepted now that severe drought was a contributor to the disappearance of the of the Khmer civilization in Angkor. And this is the first time that had been confirmed. There have been suggestions from other sources that there might have been some bad climate effects that could have contributed, but there had never been any sort of precisely dated information like what the tree rings could provide in that part of Southeast Asia.
That's wonderful and fascinating. That goes now kind of, and I'm curious of how of your work, especially with Bhutan, and how that started. Maybe a little bit on that.
Let's start in the early 1990s in Nepal. There had been a lot of interest in understanding climate variability, of course, in Asia, but not much was known about climate variability in the Himalayas, at least from tree rings. And so I got a bit of money from the National Science Foundation to go to Nepal with my colleague Paul Krusik, and we went into the Himalayas and spent several years going all around the mountains in the Himalayas, looking for old trees, which are not easy to find because deforestation in Nepal is pretty extensive, so it's very hard to find old trees. But we did. We developed a nice network of tree ring chronologies in Nepal and developed some temperature reconstructions from them. This work was published in the early 2000s. We always wanted to go to Bhutan, but Bhutan was always pretty much of a closed place. You just sort of couldn't go. Like in Nepal, you simply fly into Kathmandu and you get your visa right there in the airport, and then you're off doing almost what you want to do. You can't do that in Bhutan. You have to get permission to go there, and you have to have a visa issued to you before you can even get
board the plane.
That's right. So we were always wondering how we're going to do this, and because after we'd done the work in Nepal, it was a logical thing to go east over into the Bhutanese Himalaya to try to extend the work, our work. So just by chance, I got an email from a forest ecologist from Vienna, Austria, Georg Grotzer from Boku University in Vienna. He had been studying fir decline and mortality in Bhutan, and it wasn't quite clear what was causing it at the time. And he had seen from our work that we had a network of fir trees from the eastern Nepal Himalaya, and he said, "Well, gee whiz, would you be willing to give me let me compare your data against mine?" Well, of course, because it's not that far away. You just have Sikkim in between eastern Nepal and western Bhutan. And so sure, but I figured, well, okay, here's my chance. I said, well, gee whiz, Georg, Paul and I have been wanting to go into Bhutan. Is there any chance that you could facilitate entry for us to continue on our work in the Bhutan Himalaya as we've done in Nepal? And he says, well, yeah, I think so. So he this is back in 2001. He used his memorandum of understanding with the Ministry of Agriculture in Bhutan to bring us in to Bhutan to begin or to promote our research interests there. And we did that. We went to Bhutan in the autumn months of 2002, and started the work there. You know, we got involved with a lot of capacity building and education, teaching the foresters about tree ring analysis and that sort of thing. And then we've been returning there every year since 2002. We've been going to Bhutan.
Wow.
And I just came back actually from Bhutan this past October, having been there a month with Paul. So it's very, very different from Nepal. The forests a lot of the forest cover is intact, and there's a lot of old growth there, unlike Nepal. So we've been developing long tree ring chronologies there.
Yes.
Yeah.
So what do you think would you ascribe to the forest being intact in Bhutan versus in?
Let me just.
Sure.
Well, I think two things. First of all, Nepal, the population of Nepal at the time was around 17 million, I believe, in the 1990s. In Bhutan, was it 500, 600,000? Now, Bhutan's much smaller than Nepal, but even so, proportionally, there was a far less human impact on the natural resources of Bhutan relative to Nepal, because of much less population pressure on like the forest resources. That's part of it. And the other part is that the Bhutan at the time was a monarchy, and they had what I consider to be one of the most enlightened monarchs or kings ever, and that was the fourth king of Bhutan. He decreed that Bhutan shall always be, I think it was at least 60% forest covered. Okay, he would not. He made sure that Bhutan would never be like Nepal. Okay, so there was always a lot of control over the exploitation of the forest resource there, which has made a huge difference. And then also the fourth king set up a series of national parks and wildlife preserves and so on like that to control development in those areas even more. So he was very, very, acutely aware of the need to preserve Bhutan in a reasonably natural state, consistent with with gross national happiness of his people,
Right.
which is what he promoted as well too. But the point is, he felt like the preservation of the environment was actually an important component of gross national happiness.
Right.
And he really promoted that.
Right. And so you've done this wonderful work of creating a understanding of 638 years of kind of a weather history. Tell us a little bit more about how did you find the old trees? How did you find those trees in some ways, and then some of the challenges of doing this work?
Yeah.
And
Well, again, I'll drop back to Nepal first as a counterexample of how it was to work in Bhutan. In Nepal, Paul and I had a rule of thumb that we had to be at least 2 days' walk from the nearest village in order to find any old trees, intact forest.
really, yeah.
Because the local villages relied on the the wood for building, for firewood. And they also cut trees to open up pasture land for high altitude grazing. So they really, really overexploited the forest environment. But if you got 2 days away from the nearest village, well, it was harder to do that, you know.
Right.
And so that was our kind of rule of thumb, that we'd go that far away. And then we did find some old trees up to 1,000 years old.
Wow.
I'll show you a picture at the talk I'll give later today. But a hemlock that was over 1,000 years old, very rare, of course. But now we go to Bhutan. You can find as good or better forest only maybe an hour away from the road in Bhutan, compared to 2 days walk away from the nearest village. In other words, there's a lot of old growth forest left in Bhutan that's really quite readily accessible. Distance wise, I mean, still the terrain is very difficult, of course.
Right.
You know. But even so, it's much easier to find old growth trees to sample in Bhutan than it is in Nepal.
And what was in some ways, while you were working on this, were you willing to accept any or all kind of trees that you found were old enough, or were you looking for particular species in the region?
Well, in general, we sampled conifers only. The conifers in general will be the longest lived trees in the Himalayas. The hardwoods, tend to be shorter lived, maybe only 200 years of age, whereas the conifers could be 500 years of age. And the conifers are also much easier to sample. We use an increment borer to extract a long core of wood from the trees. We don't kill the trees. We just take this long thin core of wood out of the trees, and that's much easier, of course, for conifers. So the tree species, or the genera of conifer that we worked with were pinus, pines, fir, that's Abies, spruce, picea, hemlock, suga, junipers, junipers, and larix, for example, larch. So that covers, and there was a couple other, and there might be a couple different species within some of those genera. Like pines, there's, blue pine is in Bhutan. Blue pine is Pinus willisiana, and then there's cheer pine, Pinus roxburghii, and I know in Nepal there's Pinus roxburghii as well. I don't know if there's there is willisiana, I think, in Nepal also. But anyway, so they're the tree species.
Trees,
and,
yeah.
yeah.
And so what's come out of this analysis of 630 plus years?
Well, we're the thing that's happening in Bhutan now, and it's happening almost everywhere in the Himalayas, very rapid glacier retreat. And the belief or the understanding is that, well, with warming temperatures, if accumulation doesn't keep up fast enough with warming temperatures, the glaciers will melt and they'll retreat back up the mountains. And so that's one of the main things we were interested in doing, was trying to figure out what's the long-term pattern of summer temperature variability look like in the past, and how might that relate to what's happening to the glaciers today in Bhutan. And that was the purpose of working on this reconstruction, was provide a record of temperature variability. This is summer temperature variability now, because that's what really matters to the glaciers with respect to melt. And how might this inform us about how unusual the glacier retreat is now compared to the past, as a basis for how warm it is today compared to the past. And that's turned out to be quite an interesting story. It has very practical considerations too, because as the glaciers retreat in Bhutan, they form what we call these glacier these meltwater lakes.
Yeah.
that create these hazards called glacier lake outburst floods.
Right.
The poorly consolidated moraines burst. They get overtopped by the meltwater, burst, and massive quantities of water go down the valleys. And there's a very famous zong in Bhutan called the Punika zong, and it's really one of the most revered places in Bhutan. There's a monastery there, Buddhist monks there, and the royal family stays there at times. It was almost wiped out by a glacier lake outburst flood, or GLOF, in 1994.
Wow.
So there's an acute awareness of this hazard. Taking out both villages, of course, along the waterways that the flood is coming down, but also with respect to possibly wiping out a priceless, cultural landmark. The Punika Zong, and that's also one of the kind of these side benefits of getting to understand this better is to say, well, has this happened in the past? Has it likely been happened in the past, these kind of glacier lake outburst floods, or is it pretty well a unique new phenomenon because of climate warming?
Right. That's fascinating. And I'm kind of curious of, would you be interested in expanding your work across the Himalayas, or what's the vision of this work in the
Well, there's certainly room for expanding across. I mean, the glacier retreat is a widespread phenomenon. The one place where it's not happening to speak of is in the Karakoram of northern Pakistan. It's kind of known as the Karakoram anomaly. It's one of the few places in the world where glaciers are either not retreating or even advancing. And there's lots of speculation as to why that might be. But that's one place where it doesn't seem to be a problem or a hazard at this point. But anywhere in Nepal, and certainly in the Indian Himalaya, too, there must be that same problem, too. The glaciers are rapidly retreating, and so it'd be possible to do the same kind of research in other locations in the Himalaya without question.
Yeah, it would be fantastic to see if there was this network of tree rings across the kind of the Tarai, the mid hills, and the high Himalayas, and see if there is a variability within the three as well.
Yeah, I'm sure there would be to some degree. There is some. The Himalayas are complicated.
Very much.
Terrain. So you might expect that some areas will be behaving differently than other areas with respect to glacier retreat and so on like that. But only if by doing a detailed study, across the range of the Himalayas could you begin to understand exactly how variable, spatially variable this phenomenon is. This glacial retreat variable. Nowadays, the satellite records, of course, provide an awful lot of information about what's happening there.
Right.
We'll say since 1980, 81, roughly speaking, there's that's how far back you can go with satellite. you can actually pull out information about glacier advance and retreat in the Himalayas, but that only takes you back to basically 35 years.
Right.
Some
of these dynamics could be 100 years.
Yeah, that's right. Yeah, because glaciers have an inertia, have a long-term inertia.
Right.
They don't just immediately zip back or go ahead. You need to have this longer-term perspective, and the trees provide that. The other thing that one can do also is you can go to the moraines produced by these mountain glaciers, and you can actually just take samples of rock from these moraine boulders. If they have quartz in them, and most of them do, cosmic rays strike the quartz and cause a buildup of what's called beryllium-10. It's an isotope of that can be measured. And a colleague at Lamont, Jörg Schaefer, has actually developed in a very, very precise way of estimating how long a moraine boulder has been exposed to the atmosphere and being bombarded by cosmic rays, and you can use that as a base for estimating how many years ago that rock was uncovered as the glacier retreated up the valley. And that's really revolutionizing also our understanding of these kind of episodic advances and retreats that leave moraines behind. And you can use that also to understand the history of that. But it doesn't give you kind of a continuous record. It just gives you the snapshot period. Well, in 1643, plus or minus 20 or 30 years, we know that this moraine was uncovered by a glacier retreat, and that sort of thing,
Yeah.
So very, very useful in other ways to create a history of glacier advance and retreat in the Himalayas and also elsewhere in the world too, where there's these moraines
Getting exposed to.
Yeah.
Fascinating. And this is such a great work. I really appreciate your work.
Yeah.
Question for people who are really interested in this kind of work. How do people engage with your work? What are the possibilities for people to work with the kind of work that you're doing?
Well, I guess one way to do it, of course, is to enroll in a we'll say a graduate research program, say at Columbia University. That we have right now, for example, 3 graduate students, PhD level graduate students working in our lab. They're not studying glacier advance and retreat per se, but other things like climate variability in Mongolia, for example, is one of the cases. And we have an Indian student from Kerala who is doing some very interesting things too. But that's one way to get potentially get engaged. I should also say that Lamont Doherty every October has an open house on a Saturday, and it's possible to visit the tree ring lab, so if you have any opportunity to be down in the vicinity of Lamont on that Saturday when the open house is happening, it's possible to get a tour. You can just walk around to these different divisions, different research groups, and see what's going on, and that includes the tree ring lab.
Yeah.
So that's another way to kind of. But also, we're on email. You can always, send emails and ask for papers. We send PDFs of papers out that we've published on that sort of thing. So, we're as open as we can be to the public for sure.
Great. Well, thank you so much, and this was a wonderful talk.
My pleasure.
Yeah.
Thank you very much. Appreciate it.